Well, this is it, the absolute last video I'm going to make for this school year. So thanks for hanging with me through all of this very, very strange um, and uncertain times. Miss seeing you guys, miss being with you in class. Wish we could be finishing this up together, but it's good to get to the end nonetheless. All right, so yesterday we talked about sequences and how sequences in general are terms that follow a specific pattern. And then we talked about what it means to be an arithmetic sequences. And in that case, the pattern that is followed is a pattern of addition. And so in our last lesson, we are going to talk about another kind of pattern, right? So addition, and that is called a geometric sequence. And a geometric sequence follows a pattern of multiplication. And just like yesterday, we talked about how addition could take the form of both, positive increase, but it also could be negative because that's just adding a negative number, which is what subtraction is. Multiplication covers division as well, all right, because sometimes you multiply by a number that's greater than 1, and then that sequence is going to grow and that's going to make things bigger. But you can also say that division is multiplication by the reciprocal. And so just like subtraction is really just the adding of a negative number, division is just the multiplication of a reciprocal number. Therefore, geometric covers both what looks like multiplication and what looks like division. So there are the two formulas for, for geometric sequences. Just like we had two formulas for arithmetic, we have two formulas for geometric as well. And so we've got explicit and we have recursive. The explicit format starts with A1, just like it did with the arithmetic sequences, but then it's followed by multiplication instead of addition. Okay, so remember yesterday it was A1 plus D. This time it's going to be multiplied. And the multiplication is by the letter R. Okay, we'll talk about what R means. Then we need n minus 1, and n minus 1 is the power as the exponent n minus 1. That is the explicit formula that will create a pattern based on multiplication. The recursive formula, a sub n, will be a sub n minus 1, so that's the subscript, times R. And then we also have to identify what the first term is, like you always need to do within a recursive. And so then you will clearly state what the first term is in the pattern. And then you follow it by repeated multiplication over and over and over again. All right, so what does R stand for? In yesterday, we had the letter D. D stood for difference. And it was the difference between arithmetic terms. And so it was always consistent. Every term had the same difference between them. R stands for ratio, and it is the ratio between geometric terms. It's the pattern that you're multiplying by, or multiplying by the reciprocal if it looks like division. So you should be able to tell from a sequence of numbers what the pattern or the multiplier is. So let's look at a couple geometric sequences. Remember, these formulas only work if the pattern is multiplication. So here's our first sequence, 3, 6, 12, 24, 48, dot, dot, dot. So it's a never-ending sequence. It's an infinite sequence. Well, it wouldn't take you too long to notice that this pattern is a multiplication pattern of 2. Okay, 2 is the multiplier, or 2 is what's called the ratio between any two geometric terms. Okay, ratio means division, so I should be able to pick any two of these terms and divide them, and I should get 2. All right, so if I pick these two, 12 divided by 6, yep, that's 2. If I pick any other two, let's pick these two, 48 divided by 24, yep, that's 2. So the common ratio between all of these is 2. So I can write my explicit formula. So the explicit formula will be a sub n is a sub 1, which is 3, times the ratio, the multiplier, which is r, to the n minus 1. That formula would allow me to jump farther ahead through to any term in the sequence. I could find the 100th term. So if I wanted to find the 100th term, a sub 100, I would drop 100. Whoops, I just noticed that I didn't put 2 in for my r. You probably had it right on your notes. All right, there we go. That should be 2. And then we have 2, and then we drop 100 here, 100 minus 1. So that would be 3 times 2 to the 99. And I'd for sure want my calculator so that I could evaluate that. That would give me the 100th term, which is going to be really large in this sequence. If I want the recursive formula, it would be written this way. We start with the 3 times a sub n minus 1. Did I write that right for you guys up here? Oh yeah, I have it backwards. Let's fix it. A sub n minus 1. Here we go. And then times the r, which is 2, the multiplier. And then the 3 is the first term. So a sub 1 equals 3. That's how you'd write a recursive formula. The disadvantage of that is that you have to go in order. And it'll be start with 3, and then multiply by 2, and then multiply by 2 again, and multiply by 2 again. But you have to stay in order. Okay, part B. Here's another sequence. 10 to the negative third, 10 to the negative first, 10 to the positive first, 10 to the third, 10 to the fifth, dot, dot, dot. All right, is this a geometric sequence? Well, I should be able to pick any two terms, check their division, and see what their ratio is. So I'm going to pick two terms at random. I'm going to pick the last two. 10 to the fifth divided by 10 to the third. Hopefully you remember from Algebra 1 that you subtract the powers, so 5 minus 3, and I get 10 squared. Would that work for another set that I pick? Well, let's pick these two. 10 to the first over 10 to the negative first. Subtract their powers. That would be 1 minus negative 1, which would come out to be 10 squared. All right, so any two terms I pick, the ratio, the division, comes out to be the same. So that is my r. So I want to write my explicit formula. The first term is 10 to the negative 3. The r is 10 squared. I write to the n minus 1. That is the explicit formula. Again, I could define the 50th term or the 1000th term or the 17th term, and I would just drop a number in, and that would give me the term in the sequence. The recursive would be a sub n minus 1 times 10 squared, or you could write 100 if you wanted. And then the first term starts with 10 to the negative 3. And so that shows you that you're starting at 10 to the negative 3 and that you're consistently multiplying by 10 squared. Here's a little bit different example. What if we don't have all the terms in order? So what if we know it's a geometric sequence, and the geometric sequence has the second term to be 2, and it has the fifth term to be 54. Find R. So we kind of have some blanks. We don't know A1. We do know the second one is 2. We don't know A3. We don't know A4. We do know A5 is 54. And then the sequence would extend like that. And so our goal is to find now the value of R. Where does R come from again? Remember, R is the ratio between two terms. So let's work our way backwards. Let's take the last two terms. Okay, their ratio would be 54 over A sub 4. That should be equal to R. If I go backwards, another pair of terms, let's put a green box around them. That one, A sub 4 over A sub 3, that should also be equal to R. If I go back another set, the next pair, A sub 3 over 2, that should also be equal to R. Okay, any pair of consecutive terms in a geometric sequence should be equal to R. So what I'm going to do right now is do a little cross multiplication each time and see what we get. So I'm going to start with, I'll put a 1 here. Okay, cross multiply. I get A sub 3 equals 2R. Okay, I'll put a 1 here. I'm going to cross multiply. There, I get A sub 4 equals A sub 3 times R. And I'll put a 1 here and I'll cross multiply, and I get 54 equals A sub 4 times R. All right, now I'm going to work my way backwards. 54 equals A sub 4 times R. What does A sub 4 equal? Well, A sub 4 equals A sub 3 times R. So I'm going to substitute that in. That will give me 54 equals, instead of A sub 4, I now have A sub 3 times R times the other R. Now I'll look back again. Well, what does A sub 3 equal? A sub 3 equals 2R. So I'm going to substitute in to A sub 3. So now I have 54 equals 2R times the other R and times the final R. That's 54 equals 2R cubed. And I should be able to find R by dividing both sides by 2. It gives me 27 equals R cubed. And I cube root on both sides. That gets me R by itself equal to 3. So R is equal to 3. That's going to help me fill in all of these blanks. Okay, once I go back and I know that R is equal to 3, then I can replace all of these R's here. I'm going to erase them all with the number 3. So I'll have times 3, times 3, and times 3. So now I know that A3 is 2 times 3 is 6. Once I know that that is 6, then I can go ahead. 6 times 3 is 18. Once I know that that's 18, all right, so we have 2 here. 2 times 3 is 6. 6 times 3 is 18. 18 times that is 54. But I still don't know the first term. But I do know that the second term, that's that final pair. The second term and the first term, instead of putting a question mark, I'm going to put A sub 1. That 2 over a sub 1 should come out to be equal to r. We know that r is 3, so 2 over a sub 1 should be equal to 3. Drop a 1 and cross multiply. That's 2 equals 3 times a sub 1. Divide both sides. And so the first term must start with 2/3. And so that finally gives me the first term in my sequence. And so I can complete the sequence to be 2, starting with 2/3. So what's the overall formula for this? What is the explicit formula? The first term is 2/3. The multiplier, the r, is 3 to the n minus 1. Now I can find any term in the sequence that I want. So I want to try another one like that with you because I feel like that's a little bit of a confusing process. But if you see it twice, I think that you would really start to get the hang of it. All right, so let's have a geometric sequence. And let's suppose that we do know the first term this time, that it's 4, but we don't know the second term, and we don't know the third term, but we do know the fourth term is negative 108. And we're supposed to come up with a formula for that. We're supposed to figure out what is the ratio between those. Well, let's do the same thing. Let's work our way backwards with the last two terms that we have. So we know that negative 108 in ratio to a sub 3, that must equal r. Let's do the 2 before that. Okay, so that would be a sub 3 in ratio to a sub 2. That must also be equal to r. And then we've got our very first set, a sub 2 in ratio to 4. That must be equal to r. Each of these can be cross-multiplied if I just put a 1 under all of the r's. So I'll cross-multiply. That's going to give me a sub 2 equals 4r. If I cross-multiply again here, and that's going to give me a sub 3 equals a sub 2 times r. Well, I know what a sub 2 is from the time before. So I can say, oh, well then a sub 2 from my cross multiplication I just did. So a sub 3 must be 4r squared. And then the last cross multiplication tells me that negative 108 is equal to a sub 3 times r. Well, I know what a sub 3 is from before. And so a sub 3 is 4r squared and then times another r. So we're looking at 4r cubed. Now if I divide both sides by 4, I get negative 27 equals r cubed. And if I apply the cube root to both sides, then r by itself turns out to be negative 3. So now I know that the multiplier between each of these terms is negative 3. So I can write my explicit formula, which says, start with the first term, that's 4. The multiplier, the ratio, is negative 3. Make sure it goes in parentheses, and n minus 1. So there is the explicit formula, which would allow you to extend the sequence in an infinitely long pattern. You could write a recursive formula also. That would look like a sub n minus 1 times a multiplier of negative 3, starting with a first term of 4. And that would be the way the formula would be written as a recursive. All right, the last thing we want to work on is how to add up geometric sequences, just like we did how to add up an arithmetic sequence. And so if you have an arithmetic, let's just review that from yesterday, where you have A1, A2, A3, dot, 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 all the way to A sub n at the end. that the sum, okay, and if you wanted to do, remember our sum symbol is sigma, that would be a sub 1 plus a sub n, so the number in the front plus the number in the back, times n over 2. That was the formula we had to find the total sum for adding up arithmetic sequences. So we maybe should title this total or summation. Okay, summation means total. So what if we have a geometric? A sub 1, a sub 2, a sub 3, dot, 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 a sub n, and you know that it's a geometric. How do you find the sum of that? Well, it has its own formula. And the formula goes like this. A sub 1 times 1 minus parentheses r to the n with another parentheses all over parentheses 1 minus parentheses r. Okay, sorry. I know it feels like there's parentheses happiness going on there. That's really because of how your graphing calculator is programmed. All right, it needs all of those parentheses there in order to do what you want it to do right. So there's a large set of parentheses around every subtraction and a little set of parentheses around every r. All right, so let's try an example or two of finding the summation or the total of an entire geometric sequence. Okay, so here's your first example. Find S12 for the sequence that goes like this. 4 times 0.3 to the n. So S12 means there's 12 numbers in the sequence. It doesn't mean you have to find them all. It just means you need to know that there are 12. Now we do need to write out a couple of them. So what's the first one and the second and the third? Remember, to find a sequence, you just start plugging in 1, 2, 3, 4, 5. So when we plug in the number 1 into this particular sequence, we're going to be putting 1 in for n right there. And when we put 1 in for n, our first value is actually 1.2. Our second one, when we multiply by the ratio, which is 0.3, is 0.36. And then when you multiply that by 0.3, you get 0.108, etc. And we don't have to find them all. We just need to kind of get an idea of how it goes. And then we put the summation. We want to find the summation of all of that. Okay, well, let's use the chart, or use the formula given right here. So a sub 1 was 1.2 times parentheses 1 minus, and then parentheses 0.3 to the final n would be the number 12. So we'll put 12 here, over parentheses 1 minus parentheses 0.3 again. And if you use the parentheses correctly, you should be able to just type that directly in your calculator from beginning to end, and then come up with the answer. So why don't you practice that a minute? So you should get 1.714285. Now, how would you check your work? Well, you'd have to do it the long way. You'd have to start with 1.2 right there and add to it 0.36 and add to that 0.108, and you'd have to have all the list of all 12 numbers and add them up. And when you get to the end, you should have 1.714285. Okay? A lot faster if you know the formula. Okay, last example. You know what? This is the last example of the year, so I kind of feel like we need, something, some drum roll or something momentous here. Okay, so let's find the sum for the following sequence: 3, 6, 12, 24, ... ending with 3072. All right, I didn't make it quite as easy on you this time. First of all, is it geometric? You've got to ask yourself that question. Okay, is it geometric? Well, let's look at 3 to 6 and 6 to 12 and 12 to 24. This is geometric. It has an R value, it looks like, of 2. The next question is, how long is it? How long is this sequence? Last time we knew it was 12 units long. This time, I did not tell you how long the sequence is. I gave you the last number, which is helpful if you're doing an arithmetic sequence, but I didn't tell you how long this sequence was. So we are going to have to figure this out on our own. How long is this? Now you could do it by hand, and you could just sit there and do 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48, and you could just keep going and going and going until you get to 3072 and just keep track. That's one way. Probably a more elegant way is to set up the formula for this, the explicit formula. So the explicit formula says the last term, the nth term, would be equal to a sub 1 times r to the n minus 1. So we know the last term is 3072. The first term is 3, r is 2, and then n minus 1 is what we're trying, the n is part is what we're trying to figure out. And so we should be able to now solve this using all the math we've learned all year. So we're going to divide both sides by 3 because we're working on getting n by itself. That's 1024 equals parentheses 2 to the n minus 1. And now here's a blast from the past. How do we find that n up in that upper corner? This is easily something you might see on, say, a college placement exam that you might have to take before you start school again in the fall. How do I solve for n when it's up in this position? Well, that is going to need a logarithm because it's part of the power, and that's how we deal with powers. So we want to do a logarithm, a natural logarithm on both sides. Okay, natural log on that side, and a natural log around the 2 that has the n minus 1. The reason we do that is because the natural log allows you to pull the n minus 1 to the front. So my question becomes natural log of 1024 equals n minus 1, probably a good idea to put that in parentheses, and then ln2 by itself. We just need to get that n alone, so let's divide by the ln2. That actually works out, if you check it on your calculator, to be 10. And so these reduce away. And we have 10 equals n minus 1. Now add 1 to both sides, n is 11. Now that we know n, now we can find the sum of the sequence. So the sum of the sequence that starts with 3, 6, 12, 24, and goes all the way up to 3072, according to the formula, the sum would be the first term, parentheses, 1 minus, parentheses again for 2, and then the 11 goes there, because that's how long this is, divided by 1 minus 2. And I'd like you to pause the video, try it on your calculator yourself, and then come back and check if you have the right answer. And you're back, and hopefully you got 6141, which is the summation total of that sequence if you add up those geometric terms in order. All right, well, that wraps it up. So you'll work on this on Friday, and then next week we will review what we've been doing for the last couple weeks since spring break, and you'll take your last test of the year. And because there is no final exam, this is just our last test. and then we'll do a couple more review of trig activities to finish up next week. All right, hope you guys have a great weekend, and I'll check in with you next week.